Welcome to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The lecture series that I am covering is for the subject microprocessor. Subject code is KCS 403. Today I will be discussing Unit 5 topic, that is 8253 or 54, that is programmable interval timer. Basically, when we want to create the delays or we want to add the delays in our programming, what we basically do, we do that using the programs, using code. But this is a dedicated hardware chip for creating delays or for performing the operation same as the counters. When we can do the same job using the code, why are we using a dedicated hardware? So the answer to this question is that first of all, when we are performing the coding for the delay operations, at that time the CPU is involved in some loops, because delay cannot be created using programming without using the loops. So in that case, the CPU gets engaged, or we can say it gets occupied for the unnecessary duration into the loops. And second condition is that the delays which are generated, which are provided using the coding, are not so accurate as the delays provided by the dedicated hardwares is. So due to these two reasons, we use a dedicated hardware instead of providing the delays using programs or using code. So what is 8253 or 54? 54 is just an advanced version of 8253, and any of these two we are discussing both in combination. So these are designed, So these are designed for microprocessors to perform timing and counting functions. The difference between these two, 8253 and 8254, is that clock input up to 10 MHz for 8254 and 2.6 MHz for 8253. There are three independent 16-bit down counters in this chip. Each counter has two input pins, that is clock and gate, and one pin for the output, that is out pin. So there, for each of the three counters, there are two inputs, gate and clock, and one output, that is out pin. To operate a counter, a 16-bit count is loaded into its register. On command, it begins to decrement the count until it reaches 0. Then it generates a pulse that can be used to interrupt the CPU. So this is a very basic function of counters or delay or the timers. Now another important function is the status readback command, which is available in 8254, not in 8253, and it allows the user to check the count value, the programmed mode, the current mode, and the current status of the counter. So at any point of time, if you want to know the status of a counter, running counter, then by using the readback command, we can know the status of the counter. There are 6 programmable counter modes. I will discuss all these modes one by one in the subsequent slides. The counting can be done in two forms, that is the binary or the BCD counting. So we can say that in the binary counting, since these are the 16-bit counters, so the range of the binary counting goes from 0000H to FFFFH, and the range of the BCD counting goes from 0000 to 9999. So this is the difference between the two countings. Now single plus 5V supply is needed to run this chip, and 8254 is the superset of 8253. That is, so there are certain features which are not available in 8253 but are available in 8254. We can differentiate 8253 and 54 here. The operating frequency of 8253 is 2.6 MHz, and the operating frequency of 8254 is 0 to 10 MHz. NMOS technology is used in fabrication of 8253 and HMOS technology is used in fabrication of 8254. Readback command is not available in 8253 and it is available in 8254. As I have already discussed in the previous slide that this readback command is very important and it is used to read the status of the counter at any point of time. Reads and writes of the same counter cannot be interleaved in this case of 8253, and reads and writes of the same counter can be interleaved in 8254. This is the block diagram of 8253 or 54. Here we can see there are three counters, counter 0, counter 1 and counter 2. In each of these counters there are two inputs, that is clock and gate. So for counter 0, clock 0, gate 0 are the two inputs, and for counter 0 the output is out 0. Similar is the case with other two counters. So this is the internal bus which is transferring the data and the addresses between these modules. This is the data bus buffer in which the input is of 8 bits. This is the read-write logic control block which is having the read and write as the read-write and A0 and A1 as the 4 inputs, and another input is the chip select pin. The output of this read-write logic is going to the control word register, and in this way the control word register is connected to all the three counters, because by writing the control word register we can give the command to configure this device. So each counter has two inputs, I have already discussed here. So these are the basic features of this block diagram. Data bus buffer, it's a tri-state bidirectional 8-bit buffer which is used to interface the device to the system data bus. It has three basic functions, that is the data bus buffer is used to program the modes of 8253 or 54, it is used to load the count register and reading the count values. So these are the basic purpose of of the read-write of the data bus buffer of 8253 or 54. Another important module is read-write logic. It includes 5 signals, that is read bar, write bar, chip select bar and 2 address lines A0 and A1. In the peripheral input output mode, the read and write signals are connected to the input output read and input output write respectively, and in the memory mapped input output mode these are connected to memory read and memory write. So this device can work in any of the mode, that is the input output mapped mode or the memory mapped input output mode. Address lines and address lines A0 and A1 are used to, these are connected to the address lines of the CPU, that is our processor, are connected to the address lines A0 and A1 of 8253, and these are used to decode the address. The control word register and the counters are selected according to the signals given in the A0 and A1. How this is possible? So suppose A0 and A1 are 0, 0 and the read write are correspondingly shown here. So it represents write counter 0. Similarly, if we want to write the control word, then the status of these signals should be A0 and A1 should be 1, 1 and read should be 1. Write should be 0 and CS should be 0. So in this way the write control word can be selected. So this register is accessed when the control word register is accessed when lines A0 and A1 are logic 1. It is used to write a command word. This is very important part. Without writing the command word we cannot configure the device. Because it specifies the counter to be used, its mode and either a read or write operation. So the following table is showing all the combinations of these control signals. This is the pin diagram of 8253 or 54. So here this is the data bus D0 to D7. This is the clock. These are the input and output signals of counter 0. This is ground. Again these are the input and output signals of counter 1. Input and output signals of counter 2. A0 and A1 are connected to the address lines of the CPU, chip select, read, write and VCC. Now this is the format of the control word register and how we will select the counter using the control word register. Let's see this. So this is the 8-bit register. this SC1 and SC0 represents the which counter has to be selected. So if we want to select the counter 0, then we have to give 0 0 in both the 7th and 6th bit. Similarly, to select the counter 1, this combination should be 0 1, and 1 0 gives the combination selects the counter 2, and 1 1 selects the read back command. Similarly, here read write 1 and read write 2, these are the two bits used to control the read and write operations. If we give 0 0, it means counter latch command. That is the counter will be latched and we can read the status of the counter in that case. So it is used in the read back command. Now if we select 0 1, the read or write least significant byte only. 1 0 means read or write most significant byte only. 1 1 means read or write least significant byte first, followed by the MSB, that is the most significant byte. Similarly, now these three bits represents the modes M0, M1 and M2. So 0 0 0 represents the mode 0. So there are basically 6 modes, mode 0 to mode 5. So the combinations presented here for all the 3 bits represents the different modes. So whichever mode we want to select for our counter or timer, then we have to give the corresponding combination of bits in these 3 bit position. BCD or binary represents what is the mode of counting. If we want to give, if we want to select the binary counting, then we have to give 0 to this the bit location. Otherwise, if we want to count according to the BCD counting, then we have to give 1 to this location. So this is the control word register for 8253 or 54. The various modes of operation are mode 0, that is interrupt on terminal count. Mode 1 is hardware retriggerable one shot. Mode 2 is rate generator clock. Mode 3 is square wave generator. Mode 4 is software triggered strobe, and mode 5 is hardware triggered strobe. So let's see these modes one by one. Mode 0 is interrupt on terminal count. The name of this mode is suggesting that there should be some interrupt which is generated when the counting has reached the terminal. So it is used to generate an interrupt to the microprocessor after a certain interval. Initially the output is low after the mode is set. The output remains low after the count value is loaded into the counter. Now like here this command word is selected. Now here the counter has been loaded at this position. Clock is shown here. The gate is high in this position. So this is low as long as the counting has not come to the terminal. So as soon as the counting has reached the terminal, like counting is started here 4 3 2 1, as soon as it reaches the terminal, the out goes high. The process of decrementing the counter continues till the terminal count is reached, that is the count becomes 0 and the output goes high and will remain high until it reloads the new count. So in this case it will go high and it will remain high until some new count has been loaded into the count register. So gate signal is high for normal counting. When gate goes low, counting is terminated and the current count is latched till the gate goes high again. Mode 1, it is used as the mono-stable multivibrator. The gate input is used as a trigger input in this mode. The output remains high until the count is loaded and the trigger is applied. So even if the count has been loaded in the count register, until and unless a trigger, that is a pulse, is given at the gate, then only after the pulse arrives at the gate, then only the counting will start. And after the counting will start, the out goes low. Mode 2 is rate generator clock. The output is normally high after initialization. Whenever the count becomes 0, another low pulse is generated at the output and counter will be reloaded. So in this case, when the count becomes 0, another low pulse is generated at the output. So in this way, the low pulse is generated and the counter will be reloaded again. So in this case, mode 2 auto reload option is present in this case. In the case of a square wave generator, this mode is very similar to mode 2, except that the output remains low for half of the timer period and high for the other half of the period. So what is happening here is, after the count register has been loaded, and the gate is always high, the counting starts here, and so in this way it is being reloaded and the counting starts again. So it is on and off for equal period. So that's why it gives the square wave in this case. Another mode is software triggered mode. In this mode, the output will remain high until the timer has counted to 0, at which point the output will pulse low and then go high again. So what is happening here? Output remains high until the timer has counted 0. So until it has reached 0, like this, it has reached 0 here, then it will go low and the output will pulse low and then go high again. So the count is latched when the gate signal goes low. On the terminal count, the output goes low for 1 clock cycle and then goes high. This low pulse can be used as a strobe. So this low pulse is used as the strobe here. Hardware triggered strobe. This mode generates a strobe in response to an externally generated signal. So as far as if there is no trigger at the gate, then the counting will not restart again. So this mode is similar to mode 4, except that the counting is initiated by a signal at the gate input, which means it is a hardware triggered instead of software triggered. So the counting has to be triggered using the gate input. Then that's why it is known as a hardware triggered. After it is initialized, the output goes high. When the terminal count is reached, the output goes low for 1 clock cycle. So when the terminal count has reached, it goes for 1 clock cycle and it starts again after the gate input is triggered. What is readback command format? It is available in 8254 only, as I have already discussed. It allows the reader to check the count value, programmed mode and current status of the out pin. So this is the format of the readback command. Here this D0 is reserved for future expansion. D1 is representing the select counter 0. D2 is representing select counter 1. D3 is representing select counter 2. D4 represents the status of the latch, that is the whichever counter has been selected, what is the status of that latch. It shows that, and it gives the latch count of the selected counter, and these 2 bits are predefined. So in this way, the readback command is used to know the status of the counter at any instant. These are the various applications of this chip, that is a real-time clock, event counter, digital one-shot, programmable rate generator, square wave generator, binary rate multiplier, complex waveform generator, complex motor controller. That's all for the programmable interval timer, that is 8253 or 54. Thank you.